Hi, I'm Dave Morrissey. I was going to give the first talk, but thanks to Resh for debugging everything. So my career, I've been involved in the production of radioisotopes since I came here some years ago. And I'm going to give you an introduction to what we can do at EFRB, what we think we can do at EFRB, and what we're doing now at the NSCL. And maybe at the end a little bit about some of the open problems. Okay, so the EFRB facility is the facility for rare isotope beams. It's going to be the world-leading next-generation rare isotope production facility. We produce these isotopes by a process we call projectile fragmentation. We start with a stable beam, we break it, and then we have to separate it out using a magnetic system. So it's a completely physical separation process. And we run, at present we can run all the stable beams up to uranium. We don't run them all. But the key thing is when we do this process, we produce thousands, literally thousands of isotopes. I'll show you an example later. And the separation process, as I said, is physical, and we throw away the ones we don't want to use in the nuclear physics experiment. So the facility, the present facility and the future facility will be geared towards doing, producing a single radioactive isotope for a nuclear physics project. And then the thousands of other things that are produced along the way will be thrown away, and we're working to try and develop systems to collect the ones that are interesting and make them available. And so that's what we call isotope harvesting. The NSCL is running beams up to xenon now, sort of halfway through the periodic table, and we have some lower power uranium. And the key ingredient for the EFRB is we're going to increase the beam power, which means the production rate of the isotopes, it's just direct, by a factor of 1,000 or more. So this is why it's a dramatic increase. And so if you know the lay of the land over there, the NSCL building is on Shaw Lane, and that's kind of up front. The experimental equipment is in the middle in the high bay, which isn't so visible anymore. And then EFRB is being built underground in the back, and is moving along quite well. Okay, so we're talking about, what we would like to talk a little bit about is isotope harvesting opportunities. So, as I said, we're going to produce, for example, a rare beam for a primary user in nuclear physics, and it could be something like, is it a very heavy tungsten isotope? It's just some random isotope. From uranium, or we might produce a nickel isotope from the krypton beam as just examples. And so those primary beams will be accelerated and then brought onto a target. The target is going to be underground, and then very high power. And the first thing we do with the beam after we've run it through the target is we throw the beam away. Okay, so we want to get rid of the beam. Only a fraction of the beam, on the order of a percentage of the beam, is converted. It depends on the case. So that we have 99% of the primary beam goes into a dump. And that dump has some technical issues because it's a lot of power, but we're planning to dump it into water. And so that water is now a target for the beam, and you will have nuclear reactions, and you will make a lot of isotopes just right in the beam dump water. So that happens right away. And then the rest of this device brings the beam back up to the grade level, but along the way there are slits and apertures, magnets to separate out the fragments, so that at the end of this long chain of magnets, we have one primary user, and that person gets a specific isotope based on the nuclear physics needs. And then along the way, there are several places, in addition to the beam dump, where we'll be able to harvest out isotopes. And if you start at the beam dump, you get everything all the time. If you work further down the line in the physical separation, as you might imagine, it becomes more and more selective, and it also becomes more and more dependent on the user who's actually running. Okay, so the external user community, which is already defining the possibilities and prospects. There are workshops that have taken place. The next workshop is this summer, the end of the summer, in East Lansing at the Henry Center. If you want to go, let me know. It's an open meeting, but it's moderately small. Okay, and so EFRB is the only facility where these capabilities have been designed in. We haven't implemented the equipment, but we have the possibility. And the NSCL is actually doing the prototyping now. So this is just to emphasize the range of the thousands of isotopes. So this is nuclear physicists will recognize a chart of the nuclide's atomic number versus a neutron number. In nuclei, we have two variables, the protons and the neutrons. And so the boxes indicate all the isotopes that are produced in the water by a uranium beam. And you can see there is a function of activity. So this is a place where we're going to make all kinds of stuff. And it's a place that we imagine that people will be able to pull out different things that one could then study, how useful they might be. It's probably not a production facility. It's more a developmental facility. And this is just a photograph of we're starting on this. We have a beam gun that we're running the beam into water, and we're starting to work on this product. And then I'm not going to talk about this, so you can look at it online. This is just a list of a lot of our possible problems, research projects, different areas beyond the isotope harvesting where we're interested in talking and developing programs. So I'll leave that.
So we'll take...
Sorry.
That's okay. Take one question.
50 seconds.
That's all right. Any questions?
Sure.
David, so what kind of, it might be tough to answer, but what kind of quantities are you talking about in terms of the amount of material that might be available?
Right, so it totally depends on what you want. So if you're close to, so the black boxes for the people who haven't seen these things before, they're the stable isotopes. And so if you're relatively close to stable, then it's red, which means it's a higher yield. So we're talking about millicurie kind of levels. And in some cases it could be higher, but that's kind of the level of activity. And then as you go away from it, it goes down. So it's that kind of level. And so it's all isotopes, all half-lives, all kinds of stuff.
Sure.
Challenge.